Greetings to all. So today we will be presenting a paper that is software defect prediction using dimensionality reduction. Starting with the abstract idea of the paper here are some key points. Software defect prediction is a dynamic research issue in the field of software development lifecycle. We have done a comparative analysis of various dimensionality reduction techniques such as PCA, KPCA, IPCA, and SPCA. We have used these three different metrics for the total of 10 experiments that we have run on the two different versions of Android. The result metrics are compared using the F1 score, the accuracy, and area under the receiving operative curve. So, starting with the introduction, which can also define the need for the paper or the research that we have done, there has always been a constant attempt to develop more software-based systems with more functionalities and more reliable softwares. As we all know, the software-defined prediction reduces the time and effort to debug and test the complete software to build high-quality software. They help us identify the components of the software which are most likely to fail and helps prioritizing their debugging so that the software rate are more reliable. The machine learning and the deep learning techniques have helped solve complex and vast problems. We have attempted to utilize them to conduct a comparative study and conclude the better method for our software defect prediction. One of the key features that we have found in the problem is there are quite a dimensions and factors that are affecting the reliability of the software. Hence, the dimensionality reduction is one of the ideas that we have been taking forward to in reducing the number of dimensions or the factors that will be affecting the reliability. So, having multiple input variables in a dataset makes a predictive modeling task more challenging to the model to find which the variable is causing the issue. That is, this is the curse of the dimensionality that we talk of. Dimensionality reduction techniques help to reduce the number of input variables in a dataset. PCA is an unsupervised linear transformation technique, while KPCA or kernel PCA is an extension of PCA using kernel methods and hence a non-linear form of PCA. When in place of kernels, the extension of PCA is done using sparsity structures of features, then it's sparse PCA. Incremental PCA or IPCA that we talked about is a way of introducing the large dataset in the form of a small batches in steps or batches and hence applying PCA individually on them in form of small batches, not taking the whole thing as a one in a linear form. So we can talk about our dataset that we have used. So there are plenty of databases present online, but we have chosen a dataset that has various attributes to itself. As the more the features and more the factors, better is we could judge how the dimensional reduction is helping to work with the more dimensions and more factors that we are talking of. Hence, we have choose two different versions of Android, Lollipop Android version 5 and Marshmallow Android version 6. The dataset consists of over 25 different apps consisting of different number of classes and factors that we have included that could affect the software reliability. We used a train test split ratio of 80-20. Our dataset consists of 9,120 training data points and 2,081 test data points. The research methodology that we have used, that is the number of methods that we have incorporated uh, considering are the PCA, that is a machine learning methodology based on dimensionality reduction. It is often used on large dataset and can reduce a large set of variables into a smaller set of variables that contains the most relevant information. Kernel Principal Component Analysis, that is KPCA, is an extension of Principal PCA. It differs from PCA such that it uses the kernel methods. Sparse PCA, or the Sparse Principal Component Analysis, is an extension of PCA. It utilizes the reduction dimensionality in dataset by using structures known as sparsity structures to the features. It is used extensively in statistical analysis where the most data is sparse. Incremental PCA or IPCA is a substitution for PCA. It is used when the dataset is to be reduced and too large to be fit in the memory. It deals with a limited batch size. The whole thing that was being analyzed during the PCA is done in form of batches and not as a completely as a whole. This introduces more random and more smaller batches and better training for the model as there's limited information provided at a time. These are the dimensionality reduction techniques that are being used for the analysis part. We have been taking consider as random forest and ANN. Random forest combines the results of multiple decision trees to rule out the final result. Decision trees are supervised learning algorithms that work on the principle of information gain and entropy. These are used as classifiers in our case. Artificial neural networks also work as classifiers for us. They are inspired by the biological neural networks. They consist of various nodes that perform the unit function and hold some constant value known as weights. For the comparison of all the 10 experiments that we have been doing with the different dimensionality reduction techniques and our classifiers, there are total of 10 experiments that we'll be doing, and for comparing all these permutations and combinations, we have decided some of the performance measures that we'll be using to compare them. One of them would be the confusion matrix, or how they are well able to distinguish the correctly and how badly they are uh, predicting the wrong ones. The accuracy is the ratio. Accuracy is the second parameter that we're using, which is the ratio of correctly predicted instances upon the total number of predicted instances in the dataset. F1 score is the harmonic mean taken of precision and recall, hence the relative contribution of both is similar. The best F1 score is 1 and the worst is 0. The formula for F1 score states like 2 into precision into call upon precision plus the recall. ROC curve, which is characterized as a plot of sensitivity on the y-coordinate versus its one particularity, it's, it is characterized as a proportion of predicted non-flawed classes to the number of classes really non-flawed on the x-coordinate, is a successful strategy for assessing the quality of the execution of predicted models. This is one of the graphs, how it looks like, ROC graph that we are talking of. So for the validation, we have done a cross-validation method for validation purposes, dividing the complete dataset into training and testing datasets in the ratio of 3:1. Hence, all the entries in the datasets are used, some of which make up the training dataset, while some of them make up the test dataset. Some are used for training the classifier, others are used for finding out how well the classifier has been trained. The results that we are talking about, the results consist for all the 10 experiments that we have done, that is running the random forest independently, or we are running the ANN, or the running the PCA combined with random forest, PCA combined with ANN, KPCA combined with random forest, KPCA combined with ANN, SPCA or the sparse PCA combined with random forest, sparse PCA combined with ANN, IPCA, that is incremental PCA with random forest, and IPCA with ANN or the neural network. So once the classifier is trained on the training dataset, it is then run on the test dataset to get the required metrics for the necessary comparison between the various combinations of dimensionality reduction techniques and the different classifiers that we have told. Here the table represents the actual no, actual no, predicted yes, and predicted no, and actual yes and predicted yes. These are the uh, confusion metrics that we have found for all the 10 experiments, which was also used as a measure of comparison between them. So, for the discussion of what the conclusion that we have come up with the results is on conducting an experiment of total 10 experiments and gathering the results as listed in the results section. Solely utilizing the classification techniques did not lead to great results, as we can see in the case of RF and ANN, while working or combining with them with dimensionality reduction techniques, they are much more better and are more fruitful, which we can also see through this table that shows the accuracy, F1 score, and area under the curve scores for all the 10 experiments that we have done. We find the best of the results in the incremental PCA plus ANN. We also find that on all the cases, the ANN was better performing than random forest. We find when we train the model or when we do the dimensional reduction in batches, as in done in the cases of incremental PCA, it works much better as passing the whole thing instead using PCA, KPCA or sparse PCA. All times the batch-wise training was better and RF was not that good as compared to ANM. So we experiment with our the four dimensionality techniques and our two classifiers to conclude that the best results were in sparse and incremental PCA with combined with N. The conclusion and the future work is the results from all the combinations with ANN and the classifier had better results as compared to random forest, as the classifier PCA, KPCA, and incremental PCA coupled with ANN also displayed promising results. They used neural network with 3 layers with 6, 6, and 3 neurons respectively using ReLU and sigmoid activation functions respectively in the layers, thus concluded while handling data with large input parameters like such of software defect prediction, dimensionality reduction techniques coupled with deep learning neural networks are highly effective and efficient. In future work, we can explore furthermore techniques in dimensional reduction that we could not use were like LDA, QDA, etc., as well as other supervised and unsupervised learning classifiers that would be naive Bayes, kernel support virtual machines, etc. Here, hence, we will conclude our presentation. Thank you.